Here's a parabola represented by the two equations. One's in vertex format so that you can understand it goes through 0, 0, and ends. And we're going to pretend this parabola represents a car that accelerates, is driving at a certain speed. And based on time, it doesn't matter what time unit we do, but maybe we'll do hours at the bottom. Okay, so we'll keep the overall formula nearby, and we'll keep this like that. And we'll look at it closely. And we'll realize a couple key points. Here's 0, 0. And here's 2, 4. And here's 0, 4. Now, this on the left axis, or the y-axis, we're going to call this speed. We're going to call it kilometers per hour. Like that. And along the bottom axis, the x-axis, we're going to call that time. We're going to call it hours. Okay? And we're also, to learn what integrals are, we have to understand what derivatives are. So we're going to use just a simple, it's power rule maybe. And we're going to take the derivative. So the derivative of this thing is minus 2x plus 4. And you can tell from that derivative that it's going to form a line. It's going to form a line that goes through y is equal to 0, 4, because this is always the y-intercept. Oh, and it's downwards. It's like this, sorry, because it's negative. Downwards. And this is going to be the x and the y. And we'll discover that it's going to go through 0, 4. And if we make y 0, we discover it goes through 2, 0. So this represents here the derivative of the above. But what is the derivative? Well, the derivative of any graph is simply the slope at any given point. And it's delta y divided by delta x. And we can see here that the delta y is going to be in the units kilometers per hour. And the delta x is going to be in the units per hour. When we take kilometers an hour and divide it by hours, we get this unique thing, kilometers per hour squared. You might not recognize that unless I put it in meters, meters per second squared. This is acceleration. This is acceleration. So we learned that the derivative of this gives us an acceleration. So acceleration here is still based on time. We can see that on this axis down here, it's kilometers per hour squared. This here, it's hours. And we can also see a triangle here, and it's quite clear what the area of this triangle is. This area of this triangle is half of the height. The triangle is half times base times square. Our base is 2 and our height is 4. Half and the 2 cancel out. We're left with an area of 4. What is that? What is that area? Well, when we take the height's in this unit. When we take the length is this unit. When we multiply these things, we get kilometers per hour. Which means the total average speed from here to here was 4 kilometers an hour. This is great when we have a graph underneath here. Oh, between 0 hours and 2 hours, it was 4 kilometers an hour. And this is great when we have a graph like this where the area is very easy to use. But, what do you do when the graph is like that and you need to find the area in between? Well, that's when you can take the integral, because the integral, which is antiderivative, goes back to the speed. And we can see from here, there's a speed of 0. And from here, there's a speed of 0. And we can take the two answers to figure out what the total speed was. But let's look at the 2 hour mark instead. Oh yeah, this is from 4 over here. So really I got to do that again. It's 8. It's 8. Because this represents 4 hours later. So it's not 2, 0. Oh, let's make it 0 actually. Minus 2. No, it is 2, 0. So this represents the speed on this part of it. And this underneath the graph represents the speed coming back. Because if you look, we're going a certain speed, and at this point, we come back to our destination, don't we? Our speed reverses or becomes negative. So really, if I was to keep drawing the bottom graph, I would have a line like this, that goes to the other side, and we would have this area down here like that. Well, this area up here like that, represented in yellow, represents this area over here of this graph. And then this area over here, represented in red, represents this area here of this graph. That's because the speed is positive. And we can see from our half triangle area that it's not 8, it's actually 4. I had it right the first time. That red angle is 4. And as my point is that if that graph was not useful, the better way is to take the integral of it and realize that we're studying it to this point, the 2-hour point. And we will take a speed, we will take a reading of this. We will take point on the original graph, 0.2 minus 0.0. Well, what's the y value at 0.2? It's 4. And what's the y value at 0.0? It's 0. What's the result? 4. So we discover that the average speed during that distance was 4 kilometers an hour. Exactly what the area gave us. So what integral calculus is concerned about is it knows that that area represents the y times x. But sometimes the graph is goofy, so really we should find the integral and do this process. We find the point of time of interest minus the point of time of start, and that will give us the area of the triangle. And that's the whole point of integral calculus. It's to figure out a value of this that sometimes is difficult to measure using a very simple graph and essentially doing y2 minus y1.